Hello class, welcome to another video for this course. In this video, we are going to study section 2.7, which is about derivative of functions based on implicity. Look, in general, we first talk about implicit function and explicit function. So first I'm gonna tell you what do we mean when we say a function is something is an implicit function and something is not implicit. And then after that, we want to see how does implicit differentiation enable us to find a formula for such functions. So basically, we are looking for, the main goal is to find the derivative for so implicit functions. Okay, look at these graphs. For example, the first graph is a circle, and this circle at the left, you see the circle given by this equation: x squared plus y squared equals 16. Look at these 2 points, for example, point A and B. They are plotted by red. So as you can see, these 2 points have the same x value, but they stand at different heights. So they have same x value, different y value. For the same input, we get 2 different output. For that reason, circle fails the vertical line test, and for that reason, circle is not a function. So you know that this equation or this curve does not, the circle is not a graph of a function. Now look at the equation of this circle. It is it is x squared plus y squared. I'm sorry, I don't know what happened. So that circle is x squared plus y squared equals 16. That's the equation of the circle. And as you can see, it's a circle center at 0 and 0, radius 4. Okay, so this is 4, this is 4, x-axis, y-axis. And for example, you have the point A and point B. They have same x value, you see. So both of them have same x value, but they have different y values. They have different y values. So they fail the vertical line test because if you draw a vertical line, you see, then it intersects the circle at more than one point. For that reason, this is not a function. This is not a function. Okay, so I think everybody agree that circle is not a function. Okay, and before looking at the other graphs, because there are 2 more graphs here, let's continue our discussion about circle. Now look at the equation of this. Look at the equation of circle. Let's see. So because we know that graphically we know that this is not a function, because the graph is a circle. We can draw a vertical line that intersects the graph at more than one point, so that's not the function. But now let's look at the equation and see if there is a specific characteristic that we can connect it to for this to not be a function. So oftentimes, look, when you have a function, you have input values, and then each input value gives you an output value. So if we denote the input value with x, the output value with y, notationally, we say that f takes x and returns y. So this is the notation that we use. We say that y, or the output, is f of x. So for example, for functions, you already know that. For example, so this is the notation that we often use. We say y equal a function, a formula based on x. For example, you say y equal x squared plus 1. That's a function. Y equal 3x over e to the x plus 5. That's a function. Y equal sine of x. That's a function. So oftentimes, when you have a function, okay, when you have a function, if you represent the output value as y, then we are able to write y equal a function of x. Now, what is this function? It can be polynomial, it can be rational, it can be trig function, but whatever it is, whatever that function do to the x, it's just based on x. So oftentimes it is possible to write an equation that has the y on one side of the equation and a formula based on x on the other side. So this is explicit because we can write the equation. But let's see if we can do that here. Here, when you have circle, when you have the equation of circle, if I want to have something like this, y equal f of x, so then I should have y, the single y by itself on one side of equation. So let's try to do that. Let's try have the y on one side of the equation. So we can subtract x squared from both sides. Then we get y squared is 16 minus x squared. Okay, at this step, we have the y squared by itself on one side, but we still need to have only y. How can we get the y? Take the square root of both sides. Okay, so take a square root of both sides. Okay. But when you take the square root, what happens is that, you know what happens? Then y, because you can cross this, right? But what happens is that y is equal to positive and negative 16 minus x squared. Why? Because, look, why this is the case? Because, yes, we cross this. It's like we can cancel the square with power 2. But then when we do that, there are two possible ways. Because look, for example, this is an example, okay? For example, 2 square, if you have this, right? How can I say it? My point is that because 2 square gives me 4, negative 2 square also gives me 4, right? So y can be either positive or negative. So this is algebra. That when you take the square root, right? That could be either, for example, my point is that if you say what is a square root of 4? What is the square root of 4? Okay, a square root of 4 can be 2 and can be negative 2, because both of 2 and negative 2 square gives us 4. So when you take the square root of 4, it can be either the positive 2 or the negative 2. So every time, for that reason, every time we take the square root, the answer, so I'm gonna just put it this way. We are taking the square root of y, right? So the result, which is the square root of 16 minus x squared, it can be the positive one or the negative sign. So now, do you see the difference? Do you see the difference between that and here? There is no implicit rule, you see. So basically, when we try to solve y, as a function of x, we say y is either positive square root of 16 minus x squared, or y is the negative 16 minus x squared. Like the other functions, we don't have one implicit function. Look, we said that when you have a one function, you can say y is equal to whatever is the rule or relationship based on x. But here we are unable to do that. When you have a circle, then y can be either this one, this can be have this formula, which is positive square root of 16 minus x squared, or it can be the negative one. That is why this is not a function. So y is not a function of x. So you see, it is not like the other ones that we are able to say, okay, y is like x squared plus 1 or whatever. We have two options for y, so that's why this is not a function. Okay. I mean, we already know that the circle is not a function, but our argument, our reasoning for that was mainly graphically. But now algebraically, you can also see that this is not a this is not. So here, as you can see, we cannot write y explicitly as a function of x. So we are unable to write y explicitly as a function of x. But and that's, and what's the problem with that? The problem is that, okay, so in terms of derivative, we know that if you have an explicit, so if you can write y as a function of x explicitly, then we define the derivative. We said y prime, okay, and then we defined what do we mean by derivative, and then we introduced the rules, and using those rules, we were able to take the derivatives. But what about this case, when we are unable to write the function explicitly, we are unable to write y explicitly in terms of x. For example, look at the circle. And why do we need the concept of derivative here? Because, for example, if you fix a point, like here, if you fix a point, we are still able, graphically, we are able to draw a tangent line, right? We are able to draw a tangent line to the circle at this given point. So then we are wondering, we might be wondering about the equation of tangent line. But in order to study this tangent line or find the equation of tangent line, we need the slope. We need the slope of this tangent line. What is the slope? Slope is the derivative of y respect to x, right? But because in the circle, I am unable to write y as a function of x, as an explicit function of x. So by our methods, I am not able to find this derivative. I'm not able to find this slope, and hence I cannot, by using those, I cannot find this tangent line. So here is the situation. We have a circle, or not only circle, any curve, like look at these curves. For example, this curve, the one to the right in this picture. This is also not a function. The formula is x cubed. That one is, the graph on the right is x cubed, oh my God, x cubed minus y cubed equal 6y xy equal 6xy. And then, as you can see graphically, the graph is a curve like this. So it fails the vertical line test because when you draw the vertical line set, it cross the graph at more than 1 point. So this is not a function, right? So since this is not function, we are unable to write y as a explicitly as a function of x. We cannot do that. So how did, then the question becomes, even though they are not explicit function, is it possible to take their derivative, to compute the derivative of y respect to x? That's the question. Is it possible to take this derivative even though this is not an explicit function? And that's what we want to address in this section. Okay, so far I just tried to warm up and give you an idea of what's going on in this section. So in this section, we are wondering that if we, for like circle or for this graph with this equation, this is the equation, although they are not, although we cannot write y explicitly as a function of x, and by the way, we say that y implicitly is as a function of x, can we come up with a way to find an equation of for the derivative, differentiated? Is it possible that differentiated? So let's look at this preview activity, and then I introduce the implicit differentiation. So suppose f is a differentiable function of x. So f is a function of x, and we don't know its formula. Suppose the formula is not given. And notationally, we can either, when we talk about derivative of function f, I oftentimes use f prime. In my writing, I usually write f prime of x, but alternatively, we can use differential, d of f of x over d of x. It doesn't matter. You can either use this notation or this notation. These are interchangeable notations. Now, determine each of the following derivatives of combination of explicit function of x, the unknown function f, and the arbitrary c. Let me show you the first one. Okay, the first one, let's look at the first one. So this is the activity. And we are doing part A. The question asks to take the derivative of what? Derivative of x squared plus f of x squared plus f of x. So what does this notation mean? It means d, the d here means take the derivative of this guy, whatever is inside of the bracket, respect to x. So you are taking the derivative respect to x. Okay, respect to x. So x squared, take the derivative of x squared respect to x. It's a power function, so we can apply the rule we know about power function. The derivative is gonna be 2x. So x squared, the derivative is gonna be 2x. And then plus, so we apply the sum rule. You have two functions, take the derivative of each one, and then add them up. And then we have f of x. So the next one is, what is the derivative of f of x? The formula for f is not given. So I can just say that we just need to put here, we just need to put the derivative of f of x. I use f prime. You can also use d of the other notation. The notation is up to you. But what matters is that this is the, what needs to be written there is the derivative of f. Okay, now let's do b, x squared f of x. Okay, now b, take the derivative of x squared times f of x. So what does this notation mean? It means that take the derivative of whatever is inside of the bracket. So we should take the derivative of the thing that is inside the bracket respect to what? Respect to x. Okay, so this is x squared multiplied by f of x. So we need to apply the product rule. Product rule says take the derivative of first. So it's going to be 2x multiplied by the second one, multiplied by f of x, plus. Now take the derivative of the second function, so f prime, and multiply it by the first function, multiplied by x squared. So I just applied the product rule. Nothing new here. We just want you to get used to the notation and also see that even though the formula for f is not given, we can just put it as f or f prime. Okay, the c. Okay, c is constant plus x plus f of x squared. Okay, take the derivative of constant plus x plus f of x squared. Okay, so again, because we have addition, right? We have addition, we need to apply the sum rule. Sum rule says take the derivative of each one. Derivative of constant is 0. Derivative of x is 1. And now f of x squared. So here I need to apply chain rule. Okay, so that's gonna be, because it is f of x squared, so it's gonna be the derivative of inside function, which is f prime, multiplied by, now take the derivative of outside function, it's a square power 2, so it's gonna be 2 times f of x. Okay. And this one is f of x squared. Okay. Take the derivative of f of x squared. Okay, here we need to apply chain rule. What is the inside function is x squared. So the derivative is gonna be 2x multiplied by, what is the outside function is f. 2x multiplied by f prime of the input. So here we just applied a chain rule. And the last one, part E, is take the derivative of x f of x times f of x plus f of c of x plus cf of x. Okay. Okay, c is constant. Now, okay, so it's gonna be, there is a summation, so we apply sum rule. Okay, I'm gonna go one by one. Here we have the product, because it's a multiplication, so we should apply the product rule, which is gonna be derivative of the first times the second function plus derivative of the second times the first function. Okay, so this is just that derivative. Now, plus. Now, let's take the derivative of f of c of x. So we need to apply the chain rule. C of x, c is a constant. What is the derivative of c of x? Is just a c times f prime of c of x. And finally, plus, this one is c constant multiplied by f of x. So we just carry the constant and we take the derivative of f of x, which is f prime of x. Okay. So now we are ready to introduce implicit differentiation. So we started the exploration of this idea by the circle example, x squared plus y squared equals 16. Let's revisit that example again. so the circle with the equation of x squared plus y squared equals 16. Center is origins, radius is 4. How can we find a formula for d of y respect to d of x? That's the question. How can we find dy respect to dx? That means, what does it mean? This means, just a moment, please. Okay, so we are looking for derivative of y respect to x. But how can we, for example, when we have the circle, which is not a function, which is y is not an explicit function of x, how can we calculate such derivative? Okay, it is possible to do it by implicit differentiation. Think about it this way. Y, so although y is not, cannot be written as a explicit function of x, but look at this equation, x squared plus y squared equals 16, and remind yourself that in terms of function, you have input and output, right? And when you're taking the derivative respect to x, that's the respect to the input value. So that means in these equations, consider x as because you're looking for the derivative of y respect to x. So consider x as the input as in other words, the independent variable, and consider y as the dependent variable. So think about this, that y depends on x. And while you're keeping that in mind, take the derivative of both sides. So I mean that you have an equation. Take the derivative of this equation. You have this equation, x squared plus y squared equals 16. Take the derivative of this equation respect to x. But when you do that, keep in mind that x is the input, x is the dependent variable, and y, what is y? Y depends on x. Okay, so we need to take the derivative of x squared plus y squared, which is gonna be the same as the equal to derivative of 16, right? Okay, so when you do that, what is the derivative of x squared? So if x squared is just a variable, right, the independent variable, the derivative is gonna be 2x. That's it. Now, plus, what is the derivative of y squared? Okay, y squared is dependent on x. So y, I mean, kind of in your mind, think about y as a function of x. I know that we cannot write y as an explicit function of x, but in your mind, think about it as y as a function of x, and then take the derivative. So, okay, so it's gonna be 2y, so it's gonna be 2y, right? So it's like you need to think about this, that imagine y is f of x. So if y was f of x, you would take the 2 f of x times derivative of f of x. So here we also need to multiply it by derivative of y. Why? Because y is not dependent. It's not independent. It depends on x. It's like we also need y prime, which is f prime of x, right? So it's like you have f of x square. Do you remember how did we take the derivative? We said 2 times f of x and then multiply by derivative of f of x. So this is something like that. and equal derivative of 16 respect to x. There is no, this is constant. Respect to x, this is constant. So the derivative is 0. So as you can see, by differentiating the equation in this sense, then we end up with an equation that contains y prime, derivative of y. And that's what we are looking for. We are looking for the derivative. By the way, you can denote the derivative either by this notation or y prime. That's, I mean, I usually use y prime, but technically, what do we mean by y prime? Notationally, we mean differentiation of y respect to x. Okay, so that's what we are looking for, right? So now we can solve the equation for this. So single it out. So first subtract 2 side by 2x. So it's going to be 2y prime equal minus 2x. And then divide both sides by this multiplier, 2y. So it's going to, y prime is going to be negative 2x over 2y. And if you simplify this, you're going to get y prime is negative x over y. That's it. That's the derivative. Or in other words, dy respect to dx. This is what we are looking for, is negative x over y. So in this way, we are able to, so why this is important? Because, for example, for the circle, because it's not a function, we cannot take the derivative. But in this way, by this implicit differentiation, we can calculate the slope of the tangent line. Because, for example, if you're looking for the tangent line at this point, it has some x and y value, then you would substitute these coordinates into this, and that gives you the slope of tangent line. So that's the point. The point is that implicit differentiation enables us to come up with the tangent line, even though this graph is not a function. And if you like to go over the details of that calculation, it's also explained in your textbook. So we differentiate the equation of the circle. So we take the derivative of each element. So x squared gives us the 2x. Y squared gives us 2y. Your textbook used the notation of dy dx instead of y prime. I use y prime, but it doesn't matter. You can, they are interchangeable. You can use anyone that you like. So but at the end, this is the derivative. And you can use it in order to calculate the slope of any value. The slope of tangent line at any given point. Okay. Look at this example. In this example, for the curve given implicit, so this is the curve, right? And this curve, obviously it's not a function because look, if you look at the, we can draw a vertical line that intersect the curve at more than 1 point. So it fails the vertical line test. So it's not a function. The equation of the curve is given implicitly. X cube, let me write this down. In this example, we have x cube y square minus 2xy equals 2. Okay, that's the equation of this curve. Okay, for the curve given implicitly by this equation, find the slope of tangent line at -1 and 1. And it's also given in the graph. Look, this is the curve. The point is -1 and 1. You can see the tangent line. This green line represents the tangent line. The question is, what is the slope of this tangent line? Okay. So we know that for the recall slope of tangent line is the derivative. If it was a function, it should be the derivative of the function at that point. But this is not a function. So it's not a function that I take the derivative. However, we can use the implicit differentiation to find the y prime and to evaluate this slope. So we need to use the implicit differentiation. So take the derivative of both sides, okay? So we are gonna take the derivative of the whole thing, right? We are gonna take the derivative of x cubed plus y squared minus 2xy equals 2 respect to x. So we take the derivative of this equation respect to x. And because we are taking that respect to x, keep in mind that x is the independent variable, and y depends on x, although it's not a function, but still it depends on x. Okay, so in that sense, the derivative of x cubed is going to be 3x squared plus, what about y squared? It's going to be 2y, but because y is it's not a function, it depends on x, we also need to multiply it by y prime. Derivative of, by y prime, I mean derivative of y respect to x. Minus 2. Now here we have a product, you see, we have a product of x and y. So we need to apply product rule. So minus 2, and here I'm gonna apply the product rule. So x times y, what is the derivative of x times y? By product rule, we take the derivative of first one, which is 1, multiplied by the second one, plus, now multiply the first one by the derivative of second one. Derivative of the second one is gonna be y prime, because we are taking the derivative respect to x. So it's gonna be the derivative of y respect to x. Let me use the alternative notation. So this is gonna be dy dx. By y prime, I mean dy dx, derivative of y respect to x. Maybe because I am afraid if you say what is y prime? Y prime is derivative of y respect to x. So derivative of x, which is 1 times y, plus derivative of y, which is written here, dy over dx times x. Okay. Equal, now, what is the derivative of 2 respect to x? 2 is constant, so the derivative is 0. Let me simplify this. So I'm going to distribute the negative 2, so it's going to be negative 2y, and this is going to be negative 2x dy dx equals 0. So we are looking, what is that we are looking for? We are looking for the slope of tangent line. So a slope of tangent line at this point, for that I need the derivative of y respect to x, right? So I need the derivative of y respect to x, and I have it here and here. So let's group them. So how much do I have here? I have 2y. So look, my point is that this term and this term has the derivative of y respect to x. So factor, my point is that factor this common element. So from this we are going to have 2y, from that we are going to have next a negative 2x. Move the rest to the other side, I mean simplify the equation. It's going to be negative 3x squared plus 2y. Okay, now to have the derivative of y respect to x, we just need to divide both sides by the multiplier, which is 2y minus 2x. That's it. So we used implicit differentiation in order to calculate dy dx. Now, you want the slope of tangent line at this point, a slope of tangent line at -1 and 1. So it's so the slope of tangent line at -1 and 1 is gonna be dy dx, I mean derivative of y respect to x at for these coordinates -1 and 1. So just substitute -1 and 1 into the equation. So it's gonna be -3 times x is -1, y is +1. Y is +1 and x is -1 at this point. So now you can simplify it. So this is going to be 1. So it's going to be -3, -3 plus 2, -1. This is going to be positive, +2 plus 2 is going to be 4. So the slope is -1/4. Okay? So here is the big picture. We started with the equation. We started with this curve, right? We have the graph and we have the equation of this curve. It's not a function, but we are looking for the slope of tangent line. We need derivative, but it's not a function. So what to do? We use implicit differentiation, which means that we take the derivative of this equation, keeping in mind that x is as always it's the input, it represented independent variable, but y in this equation acts like the function of x, so it's dependent on x. For that reason, when you take the derivatives that involve y, then you need to also include dy dx. At the end, we simplify the equation to solve it for dy dx. Now that we have it in a formula, we can substitute any point to find the slope of tangent line at that point. Okay. You can also check the solution here if you want. Perhaps in your textbook, it shows more steps. Maybe I did some of them quicker. I think in your textbook shows more steps if you want to, but the answer is the same, -1/4. For example, look at this activity. Consider the curve, this curve, that defined by this equation. Look, again, it says explain why it is not possible to express y as an explicit function of x, because graphically this is not a function. We can draw a vertical line that intersect this curve at more than one point. Also, if you look at the equation, yeah, it contains y to the 4 y cube. Yeah, this is gonna, when you take the roots, it's gonna give you multiple, both positive and negative side. Yeah, it's not possible to express y as a function, write y as a function of x. So we need to, if you want to differentiate, we need to use implicit differentiation to find a formula for derivative of y respect to x. Okay, so let's do that. Let's do that. So what's the equation? It's x is y to the 5th minus 5y cube plus 4y. And we are looking for the derivative. So this is what we are looking for. Derivative of y respect to x. That's the question. What is the derivative of y respect to x? Okay, so use implicit differentiation. What does it mean? It means take the derivative of this whole thing, of this equation, respect to x. So what is that, the thing that we are taking the derivative? It's the equation, this thing. So we are taking the derivative of this whole equation respect to x. So derivative of x respect to x is 1. Derivative of y to the power of 5 is going to be 5. y to the power of 4 times y prime, or the y prime or derivative of y respect to x, because y, again, maybe in your mind think about as y a function of x, so we also need to multiply that by the derivative of minus 5. Now what is the derivative of y cubed? 3y squared times derivative of y respect to x, and finally plus 4 derivative of y respect to x. Okay, so we are looking for derivative of y respect to x. We can solve this equation for dy dx. Let's factor it. So from here, if we factor dy dx, we're gonna have what? We're gonna have, so on this side we have 1, on this side we are gonna have 5, 15 plus 4. So dy dx is gonna be, divide both sides by this multiply. 1 over is gonna be dy, the derivative of y respect to x. That's it. So we found a formula for derivative of y respect to x using implicit differentiation. Now use your result to find an equation of the line tangent to this graph at the point of 0 and 1. Okay, so tangent line at the point of 0 and 1. So what is the slope of that? A slope of tangent line at the point 0 and 1, it's gonna be derivative of y respect to x at the point 0 and 1. So that means substitute value 0 and 1 in this equation. So it's gonna be 1, 5. What is 1? 1 is y is 1. 4, negative 15. 1 square plus 4. So we just substitute the value of 1 into this equation, which is gonna be 5 plus 15 is 20, 24. 1 over 24. Okay, so that's the slope. The question is asking for a slope or equation. So we have the slope, so we are looking for the equation of tangent line. Equation of tangent line. So the equation is y equal mx plus b, a slope y-intercept. A slope is 1 over 24x. What is b? B is, okay, so now that we have the slope, and we just need to find the y-intercept for this equation. And because this is the equation of tangent line at point 0 and 1, so we know that the coordinates of 0 and 1 satisfies in the equation. So just substitute 0 and 1 here. So 1, x is 0. Then we can solve it for b. So b is 1. You see that? B is, because this is 0, so b is 1. That's it. So now we have the equation of tangent line. The answer is, the answer is y is 1/24 x plus 1. So the idea was that here, although this function, sorry, not the function. Although this graph is not a function, this graph, right? This curve is not a function, but we were able to use the implicit differentiation in order to find the equation of tangent line using implicit differentiation. Okay. I recommend you to look at the other activity. Maybe I show you a couple more examples, and then that would be all about implicit differentiation. So here says for each of the following curves, use implicit differentiation to find the derivative of y respect to x and determine the equation of tangent line at the given point. So I'm going to show you, let me show you B, because I think we already done a couple of examples similar to A, but we haven't done something like B. So let me show you B. Okay, so here we have sine of y plus y. So this is B, part B. Sine of y plus y equals x cubed plus x. So it says find, the question is, what is the question? The question is find dy dx, derivative of y respect to x, and also find the equation of tangent line. Also find the tangent line at this point. Okay, so this is, here we need to, you see, here we don't have y as an explicit function as x. But we can use implicit differentiation to take the derivative of this function. So take the derivative of this equation from both sides. Okay. So this is gonna be derivative of what happened to my whiteboard. Okay, so this is going to be derivative of sine of y plus y equal x cubed plus x. Okay, so we are going to take the derivative of this equation respect to x. When you do that, keep in mind that because we are doing respect to x, so x is the variable, x is the independent variable, y is going to be the dependent one. So y is like a function of x. So when we take the derivative of, for example, sine of y, okay, what is, so this is like chain rule, because look, this is going to be like chain rule, because y is sine of y. Derivative of sine is cosine. That's right. But y is a function of, I'm sorry, y is like a function, y is dependent on x. So the derivative is going to be the derivative of inner function, so y prime, times cosine of whatever is inside, cosine of y. Okay, plus derivative of y respect to x. So you can either use y prime, you can either use this notation, or you can write dy dx. That's up to you, which notation you prefer to use. And then take the derivative of x cubed plus x. So it's going to be 3x squared plus 1. Okay. So now what is y prime? You can solve it for y prime. From here you can factor y prime. And then you can simplify it for y prime. So it's going to be 3x squared plus 1 over cosine of y plus 1. That's it. So y prime, or in another words, dy dx is 3x squared plus 1 over cosine of y plus 1. We just calculated the derivative of this function. Not function, this equation. And then find the equation of tangent line 0 and 0. So that means we need to evaluate y prime at 0 and 0. So just substitute 0 and 0 in this equation. So it's going to be 0 squared plus 1, cosine of 0 plus 1. This is 0. Cosine of 0 is 1. So it's going to be 1 over 2. So the slope of tangent line is 1 over 2. So that's going to be the slope. And then what is the equation of tangent line? It's going to be, the slope is half. Now, I don't know what is b, but we know that it's a point at 0, 0. So 0 and 0 should satisfy in this equation. So b is 0. That's it. So the equation of tangent line is y equal half of x. Okay, got it? So we used implicit. So the idea is that you need the slope, and this is not a function, but yet you can use the implicit differentiation in order to come up with the slope of tangent line. Okay, I think the rest are similar. So I recommend you to do the exercises. Let me show you this one, for example. It says find the dy dx in terms of x and y if you have, for example, you have this relationship. So it's gonna be x squared times y. So product rule. It's gonna be derivative of x squared times the second function plus. Now, x squared times derivative of the second function. So it's gonna be times, I think here I should use the y dx notation. I guess this is the notation that it wants me to enter. Okay, so I use product rule to calculate this derivative. Rest minus, what is the derivative of x? Is 1 minus 5. What is the derivative of y? Derivative of y is dy dx. And then derivative of 0 is, derivative of 11 is 0, equal derivative of 0 is 0. So what is incorrect? Oh, the notation is not defined. So what notation do you want me to use? Y prime, should I enter y prime? No, okay. It wants me to, I'm sorry. I just took the implicit differentiation. It wants me to solve it for this. Okay, so I just did this step, right? Then, but I need to do algebra in order to simplify it, solve it for dy dx. That's right. So I didn't do these two next steps. So I should have entered my answer in this final clean way. Okay. How about here? Okay, let's do this one. Find dy dx. Yes, here you also need to apply product rule. Okay, I maybe I do it here and then I enter my answer over there. So it's x ln of x. So it's x. So it's x ln of x. Sorry, not ln of y, I guess. Natural log of y plus y cube equal 3 ln of x. So take the question is find dy dx, a derivative of y respect to x. Derivative of y respect to x. So we need to use implicit differentiation. Take a derivative of both sides of this equation. So this is gonna be product rule. Derivative of the first times second function plus first function times the derivative of second. It's gonna be 1 over y prime. Now, okay, so this was just product rule. Now take the derivative of y cubed. It's going to be 3y squared times y prime. Sorry. Times y prime. Oh my God. And then 3 natural log of x is 1 over x. The derivative of natural log of x is 1 over x. Now, now let's solve it for y prime. So it's going to be, if we factor y prime, oh, no. So it's going to be x over y prime Why did I say one? What? My bad. I'm sorry. Here, the derivative of ln of natural log of y, because this is like chain rule, because just remember chain rule. When you take use chain rule, you take the derivative of inside and it's over it. So when you have natural log of u, the derivative is u prime over u. That was the rule for natural log. Okay, so now you can factor y. From here you have x over y, and from here we have 3y squared. And here is 3, where is the x? 3 over x minus ln of y. Now divide both sides by this multiplier. So it's going to be 3 over x minus ln of y, x over y plus 3y squared. That's it. That's the answer. Let me enter the answer, see if it accepts mine. So it's going to be 3 over x. Where is it? Let me see. It's a ratio. Okay. So let's say this is the numerator and this is the denominator. Okay. Numerator is 3 over x minus ln of y. Minus ln of y. I'm not sure if this, maybe I should put it in the parentheses. Okay, I'm gonna double check that. And denominator is x over y plus 3y squared. Now preview my answer. Yes, that's what I wanted to enter. 3 over x minus ln of y, x over y plus 3y squared. Yes, that's here is what I wanted to enter. So check answer. Yeah, that's correct. Okay, so I recommend you to practice. You try to do these implicit differentiation. I leave this one for you. I leave this one for you. These are good questions. It helps you to practice the idea of implicit differentiation. And in this way, you will be ready to do the homework assignment for this section. Thank you for watching this video. I'll see you next time.